And today we're going to analyze expressions and functions that involve what is called the natural base e. Okay, so this is on your calculator. We're going to find it. So if you look in this column, you'll see a little e to the x power. Okay, that is e. And it also is here. This is e to the first. So we aren't going to use that because we're going to be plugging in different exponents. But if you press the second and then e, it's above this ln here. This actually stands for natural log. That's what we'll talk about in the next chapter. So if you do e to the first power, it will tell you what it's equal to. Okay? If you were to just do e, that is e to the first power, it's the same thing. So this is called the exponential function, and it's approximately 2.71828. This is very similar to pi, right? So pi is a decimal as well that's irrational, 3.14159, ... And what makes those two values irrational numbers? How do you know if it's an irrational number? It does what? Yeah, they're endless. Good. What else? So they have to be endless and they have to do something else. It never repeats. So like 0.3 repeating, how can you write 0.3 repeating as a fraction? No, as a fraction though. 1/3, okay? So if you can write it as a fraction, it is not an irrational number. So it's an irrational number, which means it's a never-ending decimal that does not repeat. Okay, so that is how e is similar to pi. They're both never-ending decimals that don't repeat, and they have a symbol that represents that number. Okay? Do you guys know where pi comes from? Yes. Yeah. Yeah. Did you guys do any exploratory things in geometry with that? Oh, okay. Yeah, so just like how pi is derived from something, e is derived from something as well. This isn't something that you are going to have to memorize or know, but you might notice that this is similar to one of our equations from yesterday. So e is the irrational number that you can find when you evaluate 1 plus 1 over n to the power of n. Okay, so kind of similar to our formula that we talked about when we were compounding interest. And you evaluate that when n approaches infinity. We're not going to do anything like that this year, but that is something that you'll look at towards the end of pre-calculus, and definitely something that you'll do in calculus. It's called limits. So you see what happens is things approach infinity or negative infinity. Okay, now E is a base. So if you notice when you press that first button, E to the X, you automatically got an exponent here, or you got the little caret symbol so that you could put in an exponent. Okay, so the base of E is always going to have an exponent. Okay, and then, so like this function is referred to as the exponential function, which is the exponential function. And there are different application formulas that contain the constant e. We're going to learn one of them today. And then as you get higher up in science, you also might see some. And then definitely in pre-calculus next year, there are several that have e in them. Okay, and those are some of the things we talked about earlier, like the decay, half-life, stuff like that. So for the parent function is f of x equals e to the x. All right, and then if you were making a table for this function, you would just plug in different values for x to find your y. Okay, so you could plug in -2, -1, 0, 1. We are going to be making some tables today. And then when you're evaluating them, what you're going to find is e to the -2, e to the -1, e to the 0. Now, e to the 0 you can do without a calculator, because anything to the 0 power is what? Anything to the 0 power is 1. Sorry. I'm having some hand issues today. And, yep, so we know that's 1, and now we know e to the first power. E to the first power is that 2.718. Okay, so we're going to use our graphing calculator today to find some values with e in it. So you can do e to the x. And then let's go back to our table set. We'll start at, well, you can start at -2. But let's make sure that that goes by ones, because I know we've been doing some different things with that. We can look at the graph. So based on the graph, there's going to be an asymptote where? Yep, at y equals 0. So it's y equals because it's horizontal. So we can put that in there. Okay, you can see it has the same shape as an exponential function. And then these are going to have like a lot of decimals in them. Okay? Alright, so for this one we are just going to draw a rough sketch. Like we talked about, this at 0, it's at 1. That is your y-intercept. Okay, it is going to be a curve. And just like with all of our other values, just like with all of our other exponential functions, the domain is what? Yep. So all real numbers, and then I'm still going to let you write it as the capital R. And then your range is going to be y, such that y is greater than our asymptote value. Okay, the only thing we're doing without a calculator today is the simplifying. This is very similar to what we did in 6.3. Okay, we're going to follow all of the same base rules. So when you're simplifying expressions, I call it the beep of death.